Right now, as you listen to these words, there is a robot the size of a small car driving across the surface of Mars, completely alone, navigating a landscape of red dust and ancient rock formations, collecting samples that may contain evidence of life that existed billions of years ago. This robot, one of several machines humanity has sent to our neighboring planet, is operating roughly 140 million miles from Earth, so distant that radio signals traveling at the speed of light take between 4 and 24 minutes to reach it, depending on where Mars and Earth are in their orbits. It makes decisions autonomously, choosing which rocks to examine, which paths to take, conducting experiments that no human has ever witnessed directly. And above it, the Martian sky glows not blue but butterscotch, tinted by dust suspended in an atmosphere so thin it's barely there at all. Less than 1% the pressure of Earth's atmosphere. This is Mars, a world that has captivated human imagination for centuries. A planet that was once warm and wet and possibly alive, now cold and dry and silent, yet still holding secrets that could answer the most profound question we can ask. Are we alone? Welcome. I'm glad you're here. This is a space dedicated to exploring the world's most fascinating facts in a calm, meditative way. A place where curiosity meets quietness, where profound truths become companions for drifting off. If you're new to these journeys, I'd be grateful if you'd subscribe and turn on notifications. These explorations continue because of listeners like you, and your presence here makes all the difference. Tonight, let's explore together a world both familiar and alien. A planet that orbits the same sun we do, yet is utterly different from our home. Let's talk about Mars, not as science fiction imagines it, but as it truly is. A place of towering volcanoes and canyon systems that dwarf anything on Earth. A world with seasons and ice caps and dust storms that can engulf the entire planet. A destination that represents humanity's next frontier, and perhaps our best chance of finding life beyond Earth. Mars is the fourth planet from the Sun, orbiting at an average distance of about 142 million miles, roughly 1.5 times Earth's distance from the Sun. This greater distance means Mars receives less than half the sunlight Earth does, contributing to its frigid temperatures. The Martian surface averages around -80 degrees Fahrenheit, with temperatures ranging from a relatively balmy 70 degrees at the equator during summer days to -225 degrees at the poles in winter. These are temperatures that would freeze carbon dioxide out of the air, and indeed, Mars's polar ice caps are partly made of dry ice, frozen CO2, layered with water ice beneath. And here's what makes Mars's temperature extremes even more remarkable. The thin atmosphere provides almost no insulation. On Earth, our thick atmosphere traps heat, moderating temperature swings between day and night. On Mars, with its wisp of an atmosphere, temperatures can vary by 100 degrees Fahrenheit or more between day and night at the same location. When the sun sets, heat radiates directly into space, and the surface rapidly cools. When the sun rises, the ground heats quickly, but the air remains cold because there's so little of it to warm. This creates a world where your feet might be relatively warm standing in sunlight, while your head remains freezing in the cold, thin air. Which brings us to understand something fascinating about Mars's atmosphere itself. It's composed mostly of carbon dioxide, about 95%, with traces of nitrogen, argon, oxygen, and other gases. But it's the pressure that's truly alien. At Mars's surface, atmospheric pressure averages about 600 pascals, compared to Earth's 101,000 pascals at sea level. This is equivalent to the pressure at about 100,000 feet altitude on Earth, well above the height at which humans can survive without pressure suits. Water cannot exist as a liquid at these pressures. It either freezes solid or boils away instantly. This single fact shapes everything about Mars's surface environment. And this leads to something equally remarkable about what this thin atmosphere means for Martian weather. Despite the atmosphere being less than 1% as thick as Earth's, Mars still has weather, winds, clouds, seasons, and the most spectacular dust storms in the solar system. Martian winds can reach speeds of 60 miles per hour or more during storms. Due to the low air density, these winds exert less force than equivalent speed winds on Earth. A 60 miles per hour Martian wind feels more like a 6 miles per hour breeze on Earth. But they carry dust, and it's the dust that makes Martian weather dramatic. Dust storms on Mars can grow to planetary scale, engulfing the entire planet in a reddish haze that obscures the surface from space. These global dust storms occur roughly once every 3 to 4 Martian years, though the mechanisms triggering them aren't fully understood. Once begun, they can last for months, reducing sunlight at the surface to a dim twilight. Solar-powered equipment shuts down, waiting for the storms to clear. The dust eventually settles, coating everything in a fine layer of iron oxide particles, the rust that gives Mars its characteristic red color. Consider for a moment the red dust itself. It covers virtually everything on Mars. Billions of years of accumulated oxidized iron particles ground from rocks by eons of weathering. This dust is fine, particles averaging just 3 microns across, small enough to remain suspended in air for extended periods, small enough to work its way into any crevice, any mechanism, any equipment sent to the surface. Every Mars mission must account for dust. It accumulates on solar panels, reducing power. It coats cameras and instruments, affecting observations. It may be toxic to humans if inhaled, containing perchlorates and other reactive chemicals. The dust is ubiquitous, inescapable, one of Mars's defining characteristics. But there's more to Mars's surface than red dust. The planet has geography as varied and dramatic as Earth's, despite lacking plate tectonics, oceans, or active weathering from water. The northern hemisphere is mostly smooth lowlands, vast plains of ancient lava flows and sedimentary deposits, some of the flattest, smoothest surfaces in the solar system. The southern hemisphere is heavily cratered highlands, ancient terrain dating back billions of years, scarred by countless impacts. Between these regions runs a dramatic elevation change, the dichotomy boundary, where the surface rises several kilometers over relatively short distances. Why Mars has this stark hemispheric difference remains an active research question. Perhaps a massive impact in the early solar system blasted away the northern hemisphere's crust, or perhaps ancient plate tectonics operated differently than on Earth. And alongside this hemispheric divide, there are the volcanoes. Mars hosts the largest volcano in the solar system, Olympus Mons, a shield volcano roughly the size of the state of Arizona, standing 13.6 miles high, nearly 3 times the height of Mount Everest. Its summit would reach well above most of Mars's atmosphere. The caldera at its peak is big enough to swallow entire cities. Olympus Mons and the other large Martian volcanoes, Arsia Mons, Pavonis Mons, Ascraeus Mons, sit atop a region called Tharsis, a vast volcanic plateau that bulges several miles above Mars's average elevation. These volcanoes formed over billions of years, growing to such immense size because Mars lacks plate tectonics. On Earth, tectonic plates move over volcanic hotspots, creating chains of volcanoes as the plate shifts. On Mars, the crust stayed put, and volcanic hotspots continued erupting in the same location for eons, building mountains of staggering height. The volcanoes appear extinct now. No recent eruptions have been detected, but they may merely be dormant. Mars could still have a partially molten interior, and volcanic activity might resume in the future, though probably not for millions of years. Which brings us to the other great geological wonder of Mars, Valles Marineris, a canyon system stretching roughly 2,500 miles across the Martian surface, up to 125 miles wide and 4 miles deep in places. If placed on Earth, it would span the entire United States from coast to coast. This is not a canyon carved by water like Earth's Grand Canyon. It formed tectonically, possibly as the Tharsis Bulge uplifted, stretching and cracking the crust. Side canyons, called chasmata, branch off the main valley, creating a complex network of steep-walled gorges, landslide deposits, and layered rock formations that record billions of years of Martian geological history. The scale of these features, volcanoes 3 times higher than Everest, canyons that could swallow Earth's largest gorges many times over, reflects Mars's lower gravity. Surface gravity on Mars is about 38% of Earth's, roughly a third. This lower gravity allows geological features to grow taller without collapsing under their own weight. It also means that impacts create larger craters, that volcanic eruptions can throw material higher, that erosion proceeds differently than on Earth. Everything about Mars's surface has been shaped by this lower gravity, creating a landscape that looks familiar enough to recognize, but different enough to seem alien. And here's what makes Martian geology even more interesting: the evidence for ancient water. Mars today is a desert world, dry to the extreme. Yet the surface is covered with features that could only have formed in the presence of liquid water. Valley networks snake across ancient terrains, resembling dried river systems. Outflow channels, some hundreds of miles long, suggest catastrophic floods that released enormous volumes of water in geologically short timeframes. Lakebeds, deltas, alluvial fans, all indicate that water once flowed, pooled, and deposited sediments on Mars's surface. This ancient water existed billions of years ago, during Mars's first billion years, a period called the Noachian Epoch. During this time, Mars had a thicker atmosphere, warmer temperatures, and liquid water on its surface, perhaps lakes or seas, possibly even a northern ocean covering much of the lowland hemisphere. Rain may have fallen, rivers flowed. Minerals formed that only crystallize in the presence of water. Clay minerals, sulfates, carbonates. Their presence in Martian rocks tells a story of water interacting with rock, chemically altering minerals in ways that require liquid water. But then, something changed. Mars's atmosphere was stripped away, likely by solar wind, charged particles from the sun, interacting with Mars's upper atmosphere and gradually removing it to space. Earth's magnetic field protects our atmosphere from this stripping, but Mars lost its global magnetic field early in its history, probably when its molten core cooled and solidified enough to stop generating the magnetic field. Without magnetic protection, the atmosphere eroded away over hundreds of millions of years. As pressure dropped, liquid water became unstable. It froze or evaporated, locked into polar ice or lost to space. Mars transformed from a potentially habitable world into the frozen desert we see today. And this leads to something equally fascinating about where Mars's water went. Some is still there, frozen in the polar ice caps. Both water ice and dry ice, layered together in deposits that record climatic variations over millions of years. More water is frozen in permafrost beneath the surface across much of the planet. Ground ice that remains stable below a dry surface layer. Radar instruments on Mars orbiters have detected vast quantities of subsurface ice, particularly at high latitudes. In some locations, ice makes up more than half the volume of near-surface material. But there's more to Mars's water story than ice. Some water molecules were broken apart by ultraviolet light, splitting into hydrogen and oxygen. The light hydrogen escaped to space. The heavier oxygen remained and oxidized iron in rocks, contributing to the rust that makes Mars red. Some water may be chemically bound in minerals, hydrated salts and clays that incorporated water molecules into their crystal structures. And some water may still exist as liquid, despite surface conditions that prevent it, in briny pockets deep underground, where pressure is higher and salts lower the freezing point. Liquid water might persist even today. This possibility, that liquid water might still exist somewhere on Mars, is tantalizing because of what it means for life. On Earth, wherever liquid water exists, life exists. In scalding hot springs, in Antarctic ice, in rocks miles underground, in the deepest ocean trenches. Water is essential for life as we know it, serving as a solvent for biochemical reactions, a medium for transporting nutrients and wastes, a participant in many metabolic processes. If Mars once had abundant liquid water, and if that water persisted for millions or billions of years, could life have emerged? And if it did, could it have adapted to survive underground as Mars's surface became uninhabitable? These questions drive much of Mars exploration. Multiple robotic missions have searched for evidence of past or present life, examining rocks and soils for organic molecules, analyzing mineral compositions for signs of biological activity, drilling into ancient lake beds to sample sediments that might contain fossilized microbes. So far, no definitive evidence of life has been found. But absence of evidence isn't evidence of absence. Mars is a planet-sized world, and we've examined only tiny fractions of its surface. The search continues. And alongside the search for life, there's the broader question of Mars's habitability. Not whether life exists now, but whether conditions were ever suitable for life to emerge. Evidence suggests that early Mars was indeed habitable, at least in some regions for some period. Liquid water, organic molecules, energy sources, all the ingredients thought necessary for life were present. Whether life actually arose is unknown, but the possibility is real enough to justify continued exploration. Consider for a moment what it would mean to find evidence of past or present life on Mars. Even if just fossilized microbes or simple organic molecules, such a discovery would be profound. It would mean life arose independently at least twice in our solar system, suggesting that life is not a unique fluke, but a common outcome when conditions are suitable. It would imply that the universe may be teeming with life, that Earth is not special in hosting biology. This would fundamentally change how we understand our place in the cosmos. Conversely, if we explore Mars thoroughly and find no evidence of life, despite apparently habitable conditions, that would also be significant. It might suggest that the origin of life is rarer than we think, that the steps from chemistry to biology are more difficult than we assume, that Earth is unusual in hosting life. Either finding life or conclusively not finding it after thorough searching would reshape our understanding. And as you settle in and listen, your breathing slowing, your thoughts beginning to drift. Imagine standing on Mars's surface, suited against the cold and thin air, looking across a rust-colored landscape dotted with rocks and small craters stretching to a close horizon. Mars's smaller size means the horizon is visibly nearer than on Earth. The sky above is not blue, but a butterscotch tan during the day, darkening to deep blue at sunset before fading to black night filled with familiar constellations, plus Earth, a bright blue star visible in the Martian sky, marking home. The sun appears smaller than from Earth, about 2/3 the size, providing less warmth, less light. Everything is quiet. No wind sounds because air is too thin to carry sound far. No life sounds because there's nothing living nearby. Just silence and stillness, and the deep strangeness of standing on another world. The Martian day, called a sol, lasts 24 hours and 39 minutes, remarkably close to Earth's 24-hour day. Close enough that human circadian rhythms could adapt relatively easily. This near match is coincidental, yet fortunate for any future human presence on Mars. The planet rotates at nearly the same rate we're accustomed to, creating familiar cycles of day and night, of light and darkness, of waking and sleeping. But the similarities end there. A Martian year, the time Mars takes to orbit the Sun, lasts 687 Earth days, nearly twice as long as our year. Seasons exist on Mars, driven by axial tilt similar to Earth's, but they last roughly twice as long, stretching through hundreds of sols each. And here's what makes Martian seasons even more interesting. Mars's elliptical orbit creates asymmetric seasons. The planet's distance from the Sun varies considerably throughout its year, from about 128 million miles at closest approach to 155 million miles at farthest. When Mars is closest to the Sun during Southern Hemisphere summer, that hemisphere experiences intense heating. Combined with the Southern Hemisphere's higher elevations and exposure, this creates the hottest temperatures on Mars and drives the planet's most powerful dust storms. Northern Hemisphere summer, occurring when Mars is farther from the Sun, is milder and longer. These orbital dynamics create a world where seasons are not just different from Earth's in length, but in intensity and character. Which brings us to understand something remarkable about Mars's two moons, Phobos and Deimos. These small, irregularly shaped bodies orbit close to Mars, particularly Phobos, which circles just 3,700 miles above the Martian surface. This is closer than any other moon orbits its planet in the solar system. So close that Phobos completes 3 orbits every Martian day, rising in the west and setting in the east, opposite to how moons normally appear to move. From Mars's surface, Phobos would rush across the sky, taking just 4 hours from rise to set, going through more than half its phases in that time. It would appear about 1/3 the size of Earth's moon, large enough to show some detail, but much smaller than our familiar lunar disk. Deimos orbits farther out, about 14,500 miles above Mars, taking 30 hours to orbit, longer than a Martian day. It rises in the east and sets in the west, as moons normally do, but moves so slowly across the sky that it remains visible for more than 2 sols before setting. It appears as just a bright star-like point, too small to show a disk even to good telescopes on Mars's surface. Both moons are dark, reflecting only a few % of the sunlight that hits them, composed of carbonaceous material similar to certain asteroids. This has led to the hypothesis that they're captured asteroids rather than moons that formed alongside Mars, though recent research suggests they might have formed from debris created when a larger moon was destroyed by tidal forces or impact. And this leads to something both fascinating and slightly unsettling about Phobos' future. Because it orbits so close to Mars, tidal forces are gradually pulling it closer. It's spiraling inward at about 6 feet per century. This doesn't sound like much, but over millions of years it adds up. In approximately 50 million years, Phobos will either crash into Mars's surface or, more likely, be torn apart by tidal forces as it crosses the Roche limit, the distance within which a moon cannot hold itself together against tidal stresses. When this happens, Mars will briefly have a ring system, formed from the debris of its disintegrated moon. Eventually, this ring will spread, some material falling to Mars's surface as meteor showers, some being lost to space. Deimos, orbiting farther out where tidal forces work differently, is slowly receding and will eventually escape Mars's gravity entirely, becoming an independent object orbiting the Sun. But there's more to Mars's sky than its moons. The planet experiences meteor showers, much like Earth, as it passes through debris trails left by comets. Mars gets dust storms, as we've discussed, but also more localized weather phenomena. Dust devils, small whirlwinds that snake across the landscape, lifting dust into the air. Cameras on Mars rovers have captured these dust devils in action, some hundreds of feet tall, spinning rapidly, moving across the terrain. They form when sunlight heats the surface, creating convection in the thin air, and they're more common and more vigorous on Mars than on Earth because of the low atmospheric pressure and strong surface heating. Clouds form on Mars too, though they're rare and thin. Water ice clouds appear at high altitudes, particularly around large volcanoes whose peaks extend well into the upper atmosphere. These clouds are tenuous compared to Earth's cumulus towers, more like high cirrus wisps, but they're clouds nonetheless. Another indication that Mars, despite its aridity, still has an active water cycle. Carbon dioxide ice clouds form at even higher altitudes during winter, particularly over the poles. And at dawn and dusk, fog sometimes forms in valleys and craters, particularly during spring when temperatures rise and subsurface ice begins to sublimate into the atmosphere. Consider for a moment the experience of seasons on Mars. During spring in either hemisphere, the polar ice cap begins to shrink as carbon dioxide ice sublimes, transitioning directly from solid to gas under increasing sunlight. This released CO2 temporarily thickens the atmosphere, increasing pressure slightly. Strange features appear near the poles during this thaw. Dark fans and spots on the ice, called spiders or Dalmatian spots, formed when sunlight penetrating transparent ice heats the ground beneath, causing gas pressure to build until it breaks through, spraying dust and sand onto the ice surface. These features are unique to Mars, manifestations of processes that don't occur on Earth, reminders that Mars, while sometimes familiar, operates by different rules. And alongside these seasonal changes, there's the question of climate variation on longer timescales. Mars's axial tilt, the angle at which its rotation axis tilts relative to its orbital plane, varies chaotically over millions of years. Currently, Mars tilts about 25 degrees, similar to Earth's 23.5 degrees. But Mars lacks a large moon to stabilize this tilt, and over millions of years, it swings from as little as 10 degrees to as much as 60 degrees or more. These variations dramatically affect climate. Higher tilts mean more extreme seasons, with polar regions receiving direct summer sunlight and becoming much warmer, potentially subliming vast quantities of ice into the atmosphere, temporarily thickening it and allowing warmer, wetter conditions. This climate variability is recorded in Mars's polar ice caps, which contain layered deposits of ice and dust laid down over millions of years. These layers vary in thickness and composition, creating a climate record analogous to tree rings or ice core records on Earth. By studying these layers, which orbiters can image in cliff faces where erosion has exposed them, scientists can reconstruct Mars's climate history over millions of years, seeing how temperature, dust deposition, and ice accumulation varied through repeated cycles of axial tilt changes. Which brings us to the fascinating history of Mars observation and exploration from Earth. Mars has been known since prehistoric times. It's visible to the naked eye as a bright reddish star that moves against the background constellations, distinguishing it as a planet rather than a fixed star. Ancient civilizations tracked its motion, noting its retrograde loops, the apparent backward motion it makes in Earth's sky when Earth overtakes it in orbit. In 1877, Italian astronomer Giovanni Schiaparelli observed what he described as canali on Mars, channels or grooves visible through his telescope. The Italian word was mistranslated as canals, implying artificial construction, and this sparked decades of speculation about Martian civilizations. American astronomer Percival Lowell championed the canal hypothesis, mapping hundreds of supposed canals and arguing they were irrigation systems built by an advanced civilization to transport water from polar ice caps to arid equatorial regions. Lowell's ideas captured public imagination, spawning science fiction stories about Mars and Martians. But improved telescopes and observations gradually revealed that the canals were optical illusions, the human eye and brain tending to connect faint, scattered features into linear patterns, especially when viewing at the limits of telescopic resolution. There were no canals, no civilization, just natural geological features and the tendency of observers to see patterns where none existed. But there's more to this story about early Mars observations than just mistaken canals. Even without spacecraft, astronomers learned much about Mars. They measured its rotation period, detected its polar ice caps, and watched them grow and shrink with seasons, observed dust storms, noted color changes across its surface that suggested seasonal processes, possibly vegetation. Spectroscopy, analyzing the wavelengths of light reflected from Mars, revealed its atmosphere was mostly carbon dioxide and extremely thin. By the mid-20th century, astronomers knew Mars was cold, dry, unlikely to host complex life, though simple organisms seemed possible. The romantic vision of canal-building Martians was dead, but scientific interest in Mars only intensified. And this leads to something equally fascinating about the era of spacecraft exploration, which began in the 1960s. The first successful Mars mission was NASA's Mariner 4, which flew past Mars in 1965, returning 21 grainy black and white images showing a cratered, moon-like surface. These images were disappointing to many who had hoped for a more Earth-like world. But they marked the beginning of robotic exploration that has continued for 6 decades. Subsequent missions, orbiters, landers, rovers, have progressively revealed Mars in ever greater detail, transforming it from a telescopic disk into a mapped, studied, increasingly familiar world. The Viking landers, which reached Mars in 1976, were the first to successfully operate on the surface for extended periods. They analyzed soil samples, searched for organic molecules and signs of life, measured weather, photographed the landscape. The Viking biology experiments, designed to detect microbial life, returned ambiguous results. Some tests suggested biological activity, others showed chemical reactions that mimicked biology without actually being alive. The consensus interpretation was that no life had been detected, but the results demonstrated how difficult it is to definitively test for life and how Martian chemistry can produce lifelike signatures through non-biological processes. After Viking, Mars exploration paused for 2 decades, until the Mars Pathfinder mission in 1997 demonstrated a new, cheaper approach to planetary exploration. Pathfinder delivered a small rover, Sojourner, which spent months exploring near the lander, analyzing rocks, testing navigation systems, proving that mobile robots could conduct useful science on Mars at relatively low cost. This success opened the way for subsequent rovers, Spirit and Opportunity in 2004, Curiosity in 2012, Perseverance in 2021, each larger, more capable, equipped with increasingly sophisticated instruments for analyzing Martian geology, chemistry, and potential biology. And here's what makes these rovers remarkable: their longevity and accomplishments. Opportunity, designed for a 90-sol mission, operated for nearly 15 years, traveling over 28 miles across Mars's surface, discovering evidence of ancient water, analyzing thousands of rocks and soils, surviving dust storms and harsh winters, finally falling silent in 2018 when a global dust storm covered its solar panels. Curiosity has been exploring since 2012, climbing through layers of sedimentary rock in Gale Crater, analyzing organic molecules in Martian rocks, measuring radiation levels, drilling samples, documenting ancient habitable environments. Perseverance, the newest rover, is collecting samples that a future mission might return to Earth, searching for biosignatures, testing technologies for future human exploration. These rovers have transformed our understanding of Mars. We now know that liquid water existed on Mars's surface for long periods, not just briefly. We know that Mars once had conditions suitable for life: neutral pH water, essential elements, energy sources. We know that organic molecules exist in Martian rocks, though whether they're biological in origin remains unclear. We know that Mars's climate has varied dramatically over time, and that water still plays active roles through frost, ice, and possibly briny flows. Each discovery raises new questions, motivating further exploration, gradually piecing together Mars's history and assessing its potential for past or present life. But there's more to Mars exploration than rovers on the surface. Orbiters circling Mars provide crucial context, mapping the planet at high resolution, tracking weather patterns, measuring subsurface ice, selecting landing sites for surface missions, serving as communication relays. Orbiters have been essential for understanding Mars globally, revealing patterns and processes that surface missions, limited to small areas, cannot see. Together, orbiters and surface missions create a comprehensive exploration program that combines broad overview with detailed ground truth. And alongside robotic exploration, there's increasing focus on human missions to Mars. Multiple space agencies and private companies have declared intentions to send humans to Mars, though timelines remain uncertain. Perhaps the 2030s or 2040s, depending on technological development, funding, and political will. A human Mars mission would be extraordinarily challenging, requiring life support systems that can sustain astronauts for years, radiation protection for the long journey through interplanetary space, propulsion systems powerful enough to transport heavy payloads, landing systems that can safely deliver large masses to Mars's surface, and return vehicles capable of launching from Mars and returning to Earth. The challenges are not insurmountable, but they're significant. The journey alone takes 6 to 9 months one way, during which astronauts would face microgravity, confined spaces, radiation exposure, isolation, and psychological stresses. Mars's surface gravity, while stronger than zero-G, is still only 38% of Earth's, and extended exposure might cause health issues, bone loss, muscle atrophy, cardiovascular deconditioning. Radiation on Mars's surface, though less intense than in interplanetary space, is still significant. Mars lacks Earth's protective magnetic field and thick atmosphere. Habitats would need shielding, possibly using Martian soil piled over structures. Food would need to be grown using Martian resources: soil, water, sunlight. Since transporting enough supplies for years-long missions is prohibitively expensive. Consider for a moment what a human Mars mission might look like. Perhaps astronauts would land near the polar regions, where water ice is abundant, close to the surface, easily accessible. They would establish a base using pre-positioned equipment and supplies landed by prior robotic missions. Solar panels or nuclear reactors would provide power. Greenhouses would grow food. Chemical plants would process Martian atmosphere and soil into breathable air, water, and rocket fuel. The astronauts would explore, collect samples, drill into promising geological formations, search for life with more sophisticated techniques than robots can employ. They would test technologies for long-term habitation, for in-situ resource utilization, for eventual expansion of human presence beyond Earth. This vision, humans living on Mars, even temporarily, represents a profound shift in human history. For all of our existence, humans have been confined to Earth. Mars would be the first foothold beyond, a second home, a backup location for humanity, and perhaps eventually an independent branch of human civilization. The practical benefits are uncertain. Mars has no obviously exploitable resources worth the cost of extraction and transport. But the intangible benefits, inspiration, challenge, the expansion of human capability and experience, might justify the endeavor regardless of economic return. And as you rest here, thoughts beginning to blur and fade, your breathing deep and regular, imagine the silence of Mars. A world without wind sounds, without rain, without the cries of animals or the rustle of plants. Just silence. Broken perhaps by the occasional groan of shifting soil or distant avalanche. The faint whisper of thin wind moving dust. The rare crack of thermal expansion in rocks. It's a quiet unlike Earth's quiet. A stillness that's deeper, more absolute. The quiet of a world where nothing lives, nothing grows, nothing moves except driven by physics and chemistry, by sunlight and gravity and temperature gradients. Yet within that quiet, there's a kind of peace, a sense of vast patience, as if Mars is simply waiting for warmth to return, for water to flow again, for life to emerge or arrive, waiting through the slow turning of the ages for something to change, for the silence to break, for a new chapter to begin. The question of terraforming Mars, transforming it into an Earth-like world with breathable atmosphere, liquid water on the surface, and temperatures suitable for life, has fascinated scientists and science fiction writers for decades. The basic concept seems straightforward. Thicken Mars's atmosphere enough to increase temperature and pressure, allowing liquid water to exist on the surface. Perhaps introduce photosynthetic organisms to produce oxygen, gradually creating conditions where humans could eventually walk outside without spacesuits. But the reality is far more complex and problematic than this simple vision suggests. Mars has fundamental limitations that make terraforming, if possible at all, a project requiring centuries or millennia and resources on a scale almost incomprehensible. And here's the first major challenge. Mars has insufficient volatile materials, gases and ices, to create an Earth-like atmosphere, even if we could release all of them. Studies of Mars's inventory of carbon dioxide, water, and nitrogen suggest that releasing everything frozen in polar ice caps, absorbed in soil, and chemically bound in rocks would create an atmosphere perhaps 10 to 15% of Earth's pressure at best. This would allow liquid water to exist in some locations at some times, but it wouldn't be breathable, and it wouldn't be stable. Without a magnetic field to protect against solar wind stripping, any artificially created atmosphere would gradually erode away over millions of years, requiring constant replenishment. Which brings us to understand something remarkable about proposals for how terraforming might theoretically proceed. One approach involves massive mirrors positioned in space to reflect additional sunlight onto Mars's polar regions, heating them, causing frozen CO2 to sublime into the atmosphere. As atmospheric pressure increases, temperature rises, creating a feedback loop where warming releases more gas, further warming the planet. This could theoretically trigger a runaway greenhouse effect, the same process that made Venus uninhabitable but controlled to create beneficial warming on Mars. However, building mirrors large enough to make a significant difference, positioning them accurately, maintaining them for centuries, all of this represents engineering on a scale humanity has never attempted. Another approach involves importing volatile materials from elsewhere in the solar system. Comets, composed largely of water ice and frozen gases, could theoretically be redirected to impact Mars, delivering volatiles and energy. Asteroids from the outer solar system, also rich in ices, might serve similar purposes. But redirecting these objects requires enormous energy and precision. Slight miscalculations could send them off course entirely or impact Mars with such force that they cause more harm than benefit. And the number of impacts needed to significantly alter Mars's atmosphere would be in the thousands or tens of thousands, a project spanning centuries. Yet another proposal involves introducing organisms, particularly bacteria and algae, engineered to survive Martian conditions and produce gases that alter the atmosphere. Photosynthetic organisms could theoretically convert CO2 to oxygen over long periods. Methanogenic bacteria might produce methane, a strong greenhouse gas that would help warm the planet. But even under optimal conditions, biological terraforming would take thousands or millions of years. And there's an ethical dimension. If Mars has indigenous life, even microbial, introducing Earth organisms would contaminate and potentially destroy those ecosystems. Many scientists argue we should thoroughly search for Martian life before considering any terraforming efforts. And this leads to something equally fascinating about the concept of paraterraforming, an alternative approach where instead of transforming the entire planet, humans create localized habitable environments under domes or underground, leaving Mars itself largely unchanged. This is far more achievable with current or near-future technology. Large transparent or translucent domes could cover craters or valleys, creating pressurized volumes containing breathable atmosphere and controlled temperature. Inside these enclosed spaces, plants could grow, water could exist as liquid, humans could live without spacesuits. Multiple such enclosed habitats could eventually cover significant portions of Mars, creating a patchwork of habitable zones without altering the planet as a whole. Paraterraforming has advantages beyond feasibility. It preserves Mars in its current state, allowing scientific study to continue without contamination. It can be implemented incrementally, building one habitat at a time as resources and population grow, rather than requiring massive upfront investment. It's reversible. If abandoned, the habitats would eventually fail and Mars would return to its natural state. And it avoids the ethical concerns of planetary-scale modification. However, it confines humans to artificial structures, never allowing the freedom of an open sky and natural landscape that full terraforming would theoretically provide. But there's more to the Mars settlement question than just environmental engineering. The social, political, and economic dimensions are equally complex. Who would govern Mars? Initially, any settlement would likely operate under the authority of whichever nations or organizations funded it. But as settlements grow and become more independent, governance questions become pressing. Would Mars remain under Earth's control, with decisions made by distant bureaucracies? Or would settlers demand self-governance, perhaps eventually independence? History suggests that colonies distant from their parent civilizations eventually seek autonomy, and Mars, separated from Earth by months of travel time, would be the most distant colony humans have ever established. Economic viability is another challenge. What would a Mars settlement produce that would justify the enormous cost of establishing and maintaining it? Scientific knowledge has value, but probably not enough to sustain large-scale settlement. Mars has no unique physical resources worth the cost of shipping to Earth. Anything found on Mars likely exists in more accessible forms elsewhere in the solar system. Perhaps Mars's value would be strategic, a hub for further solar system exploration, a testing ground for technologies, a backup for human civilization in case of catastrophe on Earth. Or perhaps economic thinking is misapplied. Maybe Mars settlement, like much of human space exploration, is motivated not by economic return, but by intangibles like inspiration, challenge, and the drive to explore. Consider for a moment what life might actually be like for humans living on Mars. Daily routines would revolve around maintaining life support systems, monitoring air quality, water recycling, power generation, temperature control. Growing food would be essential, likely in hydroponic or aeroponic systems, using artificial light and carefully controlled nutrients. Communications with Earth would always have delays, 4 to 24 minutes one way depending on planetary positions, making real-time conversation impossible. This delay would force Mars settlers to be autonomous, making decisions locally rather than constantly consulting with Earth. Over time, this autonomy would likely foster distinct Martian culture and identity. Physical adaptation to Mars's environment would create differences between Martians and Earth humans. Children born and raised in Mars's 38% gravity would develop differently. Taller, with less muscle and bone density, perhaps with physiological adaptations to lower gravity. Returning to Earth might become difficult or impossible for people who spend many years on Mars. Their bodies adapted to low gravity might not function well in Earth's gravity well. This could lead to a situation where Mars-born humans are effectively permanent residents, unable to visit humanity's homeworld. Such physiological divergence, given enough time, could even lead to speciation, Martians and Earthlings becoming different enough to constitute separate populations. And alongside physical differences, cultural divergence would seem inevitable. Mars settlers would develop their own traditions, values, and perspectives, shaped by their environment. Living in an enclosed habitat where everyone's survival depends on functioning life support, creates different social dynamics than life on Earth, where nature provides air and water freely. Mars society might prioritize collective responsibility, technical competence, and resource conservation more heavily than Earth societies. Or perhaps the opposite. The frontier mentality might produce highly individualistic culture, valuing self-reliance and innovation. Either way, Martian culture would reflect Martian conditions, gradually becoming distinct from Earth culture. Which brings us to the broader question of why humans might choose to settle Mars despite the challenges. Part of the answer is practical. Spreading humanity across multiple worlds reduces existential risk. A catastrophe that destroys Earth, asteroid impact, nuclear war, pandemic, wouldn't affect Mars, and vice versa. Distributing human civilization across multiple independent locations increases the probability that humanity as a whole survives any single catastrophic event. This argument for Mars settlement frames it as insurance, a backup copy of human civilization stored safely away from Earth's risks. But there's more to the motivation than just survival insurance. Throughout history, humans have explored and settled challenging environments not purely for practical reasons, but because challenge itself attracts certain people. The Arctic, the Antarctic, high mountains, remote islands, all have drawn explorers and settlers despite offering difficult conditions and few obvious benefits. Mars represents the ultimate frontier, the most extreme environment humans have seriously considered inhabiting. For some people, that challenge is attractive in itself, worth pursuing regardless of practical returns. The human drive to explore, to test limits, to go where no one has gone. These impulses have motivated exploration for as long as humans have existed, and Mars is simply the next horizon. And this connects to something deeper about humanity's relationship with space and our place in the cosmos. For the vast majority of human existence, Earth was all we knew. The universe beyond was mystery, accessible only through observation, never through direct experience. Space exploration has changed this. We've stood on the moon, operated on Mars through robotic proxies, sent probes to the outer solar system and beyond. But we remain fundamentally Earthbound, our species confined to one fragile world. Establishing permanent presence beyond Earth, whether on Mars or elsewhere, would mark a transition as significant as when our ancestors first left Africa, when life first crawled onto land, perhaps even as significant as when life itself first emerged from chemistry. It would be humans becoming a multiplanetary species, no longer wholly dependent on Earth, no longer confined to our birth world. But here's the truth that often gets lost in grand visions of Mars settlement. Earth is and will remain far more hospitable than Mars for the foreseeable future. Even after catastrophic damage, nuclear winter, runaway greenhouse effect, ecosystem collapse, Earth would still have breathable atmosphere, reasonable gravity, magnetic field protection, and abundant water. Mars doesn't have these things, and won't, unless we provide them through sustained engineering efforts lasting centuries. The harshest deserts, highest mountains, deepest ocean floors on Earth are all more habitable than Mars. Any environmental catastrophe, short of total planetary destruction, leaves Earth more livable than Mars. This realization doesn't invalidate Mars exploration or settlement, but it provides important perspective. Mars shouldn't be seen as an escape from Earth's problems, or a substitute for protecting Earth's environment. We must solve problems on Earth: climate change, ecosystem degradation, political conflicts, regardless of whether we settle Mars. Mars settlement, if it happens, should be an expansion of human civilization, not a replacement for Earth, not an abandonment of our home planet, but an extension of it, carrying Earth life and human culture to new places while maintaining and valuing what we have here. And alongside these grand questions about settlement and civilization, There are the immediate, practical questions that current Mars missions address. Where is the best place to land humans? Where is water most accessible? Where are the safest, flattest landing zones? Which locations offer the most interesting science? What resources are available at different sites? Answering these questions requires detailed mapping, analysis, and reconnaissance, work that robotic missions are currently conducting. Each rover, each orbiter, each instrument adds data that helps plan eventual human missions, reducing risks and identifying opportunities. Recent discoveries have refined understanding of potential landing sites. The presence of subsurface ice at mid-latitudes, detected by radar and confirmed by excavations, means water is accessible without going to extreme polar regions. Certain locations, like Jezero Crater, where Perseverance is exploring, or Gale Crater, where Curiosity has worked for years, show clear evidence of ancient habitable environments and might preserve biosignatures if life ever existed there. Other sites offer engineering advantages. Valles Marineris's deep valleys might provide natural radiation shielding, while the flat plains of Vestidas Borealis offer easy landing and surface travel. And here's what makes site selection complicated. Different goals favor different locations. If the goal is finding evidence of life, you want sites with the best preservation of ancient sediments and organic materials. If the goal is resource utilization for settlement, you want sites with accessible water, suitable soils, and reasonable solar exposure. If the goal is safety and ease of operations, you want flat terrain, low elevation for maximum atmospheric thickness during landing, and moderate latitudes to avoid temperature extremes. No single site optimizes for all goals simultaneously, so choosing landing locations involves trade-offs and compromises based on mission priorities. This complexity extends to questions about how many sites to explore, whether to concentrate efforts in a few locations or spread them across many, whether to return repeatedly to interesting sites or always push toward new territory. Current Mars exploration involves both strategies. Some rovers explore systematically across kilometers of terrain, while others drill deep in single locations. Orbiters provide global context, while rovers provide ground truth. The combination allows both broad survey and detailed investigation, gradually filling in knowledge gaps from multiple scales and perspectives. And as you rest here, your mind growing quiet, thoughts dissolving like frost under morning sun, consider how exploration changes understanding. Mars began as a point of light in Earth's sky, then became a disk showing vague features through telescopes, then a cratered surface in fuzzy spacecraft images, then a mapped world with names and features, then a place where robots have worked for decades, analyzing rocks and soils, measuring weather, photographing landscapes. Each stage of exploration added detail, corrected misconceptions, revealed unexpected complexity. And future stages, humans walking on Mars, settlements growing, perhaps life discovered, will add further layers of understanding, perhaps fundamentally changing how we think about Mars, about planets, about life's distribution in the universe. The possibility that life once existed on Mars, or might still exist in protected environments, raises profound questions about how life emerges and persists in the universe. If we were to discover even simple microbial life on Mars, fossilized or living, the next question becomes whether it originated independently from Earth life or whether it shares a common ancestry. Panspermia, the hypothesis that life can transfer between planets, suggests that rocks blasted off Earth by asteroid impacts could carry microorganisms to Mars, or vice versa. Billions of years ago, when both planets had thicker atmospheres and Mars had liquid water, conditions might have allowed life to survive the journey through space, protected within rock interiors from radiation and cold. And here's what makes this possibility so intriguing. If Martian life shares DNA or similar biochemistry with Earth life, It would suggest either panspermia or that life's fundamental chemistry is so constrained that independent origins produce similar results. But if Martian life uses completely different biochemistry, different genetic molecules, different amino acids, different metabolic pathways, it would provide powerful evidence for independent origin, demonstrating that life can emerge through multiple pathways, that Earth's particular solution to the problem of life is not the only one. Either finding would be scientifically revolutionary, but the discovery of truly alien biochemistry would be more profound, suggesting that life is common in the universe and can take diverse forms. Which brings us to understand something remarkable about the extreme environments on Earth where life persists, and what they tell us about Mars's potential habitability. Microorganisms have been found living in environments once thought sterile, in rocks kilometers underground, in Antarctic ice, in acidic hot springs, in hypersaline lakes, in the stratosphere, even in nuclear reactor cooling pools. These extremophiles demonstrate that life is incredibly adaptable, capable of surviving extreme temperatures, pressures, radiation levels, pH extremes, and desiccation. Many extremophiles thrive in conditions analogous to what Mars might have offered billions of years ago, or might still offer in protected subsurface environments. Some of the most Mars-relevant extremophiles are those living in Arctic and Antarctic environments. In Canada's high Arctic, microorganisms survive in permafrost soil that remains frozen most of the year, becoming active only during brief summer thaws. In Antarctica's dry valleys, one of Earth's most Mars-like environments, microbes live inside rocks, endolithic organisms that extract moisture from occasional snowmelt and photosynthesize using sunlight-penetrating translucent minerals. These organisms survive temperatures far below freezing, extreme desiccation, and intense UV radiation. If life exists on Mars today, it might resemble these endolithic communities, hidden inside rocks where conditions are slightly less harsh than on the surface. But there's more to the extremophile analogy than just cold tolerance. Some Earth organisms survive in salt deposits, living in tiny pockets of brine within halite crystals. Mars has extensive salt deposits, and if any liquid water exists on Mars, it would be extremely salty. Brines whose high salt concentration depresses the freezing point, allowing them to remain liquid at temperatures well below water's normal freezing point. Such brines might exist seasonally in certain locations, and if Mars has life, it might survive in these briny environments, emerging from dormancy when conditions become favorable, going dormant again when water freezes or evaporates. And this leads to something equally fascinating about Mars's methane mystery. Instruments on orbiting spacecraft and surface rovers have occasionally detected small amounts of methane in Mars's atmosphere. Methane shouldn't persist. It breaks down under UV radiation within a few hundred years, so any detected methane must have been released recently. But what's producing it? On Earth, most methane comes from biological sources. Microorganisms produce it as a byproduct of metabolism. But geological processes can also produce methane. Reactions between water and certain minerals, volcanic activity releasing trapped gases. Mars's detected methane could indicate active biology, or it could be geological, or it could be both, or neither. Perhaps contamination from Earth equipment or measurement errors. The methane detections are frustratingly inconsistent. Sometimes it's detected, sometimes not. Levels vary by location and season. Some observations show methane plumes that appear and disappear rapidly, suggesting localized sources. But confirming these detections and identifying their sources has proven difficult. The Curiosity rover's instruments can detect methane, but they've recorded it only sporadically. Orbiting spacecraft see hints, but can't pinpoint sources. This mystery motivates continuing investigation. If methane is real and persistent, understanding its source could answer fundamental questions about Mars's current activity, whether geological or biological. Consider for a moment what it would mean to discover active biology on Mars. Not ancient fossils, but living organisms. It would mean that Mars's surface conditions, despite being apparently hostile, still permit life in some locations. It would suggest that life, once established, is remarkably tenacious, capable of surviving planetary environmental collapse, adapting to progressively worsening conditions rather than going extinct. It would provide hope that even heavily degraded environments might retain biology in refuge habitats, that extinction is not inevitable when planets undergo climate change. And it would raise immediate questions about protecting that life from contamination by Earth organisms arriving on spacecraft. Planetary protection protocols already govern how spacecraft are cleaned and sterilized before launch to Mars. The goal is to prevent Earth microorganisms from hitchhiking to Mars and either contaminating environments where Martian life might exist or interfering with measurements searching for life. Spacecraft headed to Mars are assembled in clean rooms, sterilized with heat or chemical treatments, and monitored for biological contamination. Areas of Mars considered special regions, locations where liquid water might currently exist, are off-limits to spacecraft that haven't undergone rigorous sterilization. These protocols balance scientific exploration with protection of potential Martian ecosystems. But there's more to planetary protection than preventing forward contamination, bringing Earth life to Mars. There's also backward contamination, bringing Martian material to Earth. Any sample return mission must ensure that Martian samples cannot contaminate Earth's biosphere. Even if the probability of Martian organisms being harmful to Earth life is vanishingly small, the consequences, if they were harmful, could be catastrophic. Sample return missions plan multiple levels of containment. Samples sealed in containers on Mars, transferred to Earth in sealed capsules, opened only in specialized biosafety facilities designed to prevent any escape of material. These precautions may seem excessive, but they reflect appropriate caution when dealing with unknown biology from another world. And alongside these practical considerations about life detection and protection, there's the philosophical dimension of what finding life on Mars would mean for humanity's self-understanding. For all of recorded history, humans have wondered whether we're alone in the universe. Religious and philosophical traditions have proposed various answers, but empirical evidence has been absent. Finding life on Mars, even simple microbes, would provide that evidence, definitively answering that life exists beyond Earth. The implications would ripple through philosophy, theology, science, and culture. How we understand our place in the cosmos, whether we see Earth as special or typical, what we believe about life's prevalence and meaning, all would be affected. Conversely, thoroughly searching Mars and finding no life would also be significant. If Mars, despite having had abundant liquid water and apparently habitable conditions for millions or billions of years, never developed life, it would suggest that life's origin is rare, that the steps from chemistry to biology are difficult, that habitable conditions alone aren't sufficient. This would imply that Earth might be unusual, that life-bearing worlds might be scarce in the universe. Such a finding would be sobering but valuable, calibrating our expectations about astrobiology and focusing attention on understanding what makes life's origin possible or probable. Which brings us to the broader context of Mars within astrobiology, the study of life in the universe. Mars is one of the most accessible places beyond Earth where life might exist or might have existed. Venus's surface is too hot, Mercury too small and too close to the Sun, the Moon too dry and airless. Beyond Mars, there are promising locations. Jupiter's moon Europa with its subsurface ocean, Saturn's moon Enceladus, also with liquid water, Saturn's moon Titan with liquid methane lakes and complex organic chemistry. But these are much farther away, harder to reach, more difficult to explore. Mars is close, familiar, accessible with current technology. It's humanity's best current opportunity to search for life beyond Earth, which is why so much attention and resources focus there. The coming decades will likely provide answers to questions that have tantalized humanity for centuries. Multiple Mars sample return missions are planned or underway. Perseverance is collecting samples that a future mission might retrieve and return to Earth for detailed analysis. These samples, analyzed in laboratories with instruments far more sophisticated than anything we can send to Mars, might contain definitive evidence of past life, or definitive evidence of its absence. Human missions to Mars, if they occur, will allow even more thorough exploration, with human judgment and flexibility augmenting robotic capabilities. The mystery of Martian life may finally be solved, one way or another, within the next few decades. And here's what makes the search for life on Mars particularly poignant. Mars had its chance. Billions of years ago, it had conditions that might have allowed life to emerge. Liquid water, organic molecules, energy sources. If life began, it had hundreds of millions, perhaps billions of years to establish itself, to evolve, to adapt. But then, Mars lost its atmosphere. Surface water froze or evaporated. Temperatures plummeted. Radiation levels increased. If life existed, it faced a choice: adapt to progressively harsher conditions or go extinct. Did Martian life successfully adapt, retreating underground or finding other refuge habitats where it survives today? Or did it go extinct, leaving only fossils as testament to its existence? Or did it never emerge at all, leaving Mars forever sterile, despite having habitable conditions? These questions about Mars's biological history connect to broader questions about planetary habitability and the factors that determine whether planets remain habitable over long periods. Earth has remained habitable for billions of years. But why? What makes a planet maintain habitable conditions over geological timescales? Clearly, size matters. Mars's smaller size meant it cooled faster, losing internal heat that drives geological activity. This cooling allowed the core to solidify, shutting down the magnetic field that protected the atmosphere. Without magnetic protection, solar wind stripped away the atmosphere, and without atmosphere, liquid water became impossible. Earth's larger size has allowed it to remain geologically active, maintaining its magnetic field, retaining its atmosphere, continuing to support liquid water and life. But size isn't everything. Venus is nearly Earth's size, but completely uninhabitable due to runaway greenhouse effect. Distance from the Sun matters. Venus receives more solar energy than Earth, contributing to its extreme temperatures. But distance alone doesn't determine habitability. Mars receives less solar energy than Earth, yet was once warmer and wetter than it is today. The interplay of factors, size, distance from star, atmospheric composition, geological activity, magnetic field, solar wind intensity, all contribute to whether a planet is habitable and remains so. Understanding these factors on Mars helps us understand habitability generally, applicable to exoplanets around other stars. And alongside scientific understanding, there's the emotional and aesthetic dimension of Mars, what the planet represents in human imagination. Mars has inspired countless works of fiction, from H.G. Wells's War of the Worlds to Ray Bradbury's Martian Chronicles, to Kim Stanley Robinson's Mars trilogy, to recent films and novels. These works explore themes of exploration, colonization, environmental transformation, contact with alien life, and human nature tested in extreme environments. Mars serves as a canvas for projecting human hopes and fears, a setting for imagining futures different from our present. The real Mars, as revealed by science, is in some ways less romantically interesting than Mars of fiction. No canals, no ancient civilizations, no obvious life. But in other ways, the real Mars is more interesting. a world with a complex history recorded in its rocks, with geology that dwarfs Earth's in scale, with ice caps and dust storms, and the possibility of microbial life hiding in protected niches. The real Mars rewards close attention, revealing subtle wonders that speculation alone cannot match. Fiction imagines Mars as we wish it to be. Science reveals Mars as it actually is, which often proves stranger and more nuanced than imagination predicted. Consider for a moment the trajectory of human understanding of Mars. From ancient observations tracking its motion through the zodiac, to telescopic observations revealing polar caps and seasonal changes, to spacecraft images showing craters and canyons, to rovers analyzing rocks and searching for signs of past water, to future missions that may discover life or establish human presence. Each stage has built on previous understanding, sometimes confirming expectations, sometimes overturning them, always adding detail and complexity. This progression from ignorance to knowledge, from speculation to evidence, from distance to intimacy. It's one of science's great achievements, transforming Mars from a mysterious light in the sky to a world we know in increasing detail. And yet mysteries remain. The origin of Mars's hemispheric dichotomy, why one hemisphere is low and smooth while the other is high and cratered. The fate of Mars's water, how much remains and where. The possibility of life, past or present. The future of Mars, whether it will be explored by robots alone or also by humans. Whether it will be studied in its natural state or transformed through terraforming. Whether it will remain forever an object of study or become a home for human civilization. These mysteries motivate continued exploration, ensuring that Mars will remain a focus of scientific attention and public fascination for decades or centuries to come. And as you drift now into deeper rest, your thoughts dissolving into the formless quiet that precedes sleep, imagine the vast darkness of space, and within it, a small red world, cold and quiet, circling the sun, waiting for storms to pass, for seasons to change, for ice to sublimate and reform, for whatever comes next in its long history. Perhaps robots will continue exploring, analyzing, photographing, sending data back to Earth. Perhaps humans will arrive, establishing bases, conducting research, testing technologies for living beyond Earth. Perhaps life will be discovered, revealing that Mars's silence conceals persistent biology adapted to harsh conditions. Or perhaps Mars will remain as it has been for billions of years, geologically active in slow ways, climatologically dynamic over long timescales, but biologically barren. A world where life never emerged, or emerged and went extinct, leaving only rocks and dust and ice and the faint whisper of wind in the thin air.